So hello everyone, welcome to this seminar, the sixth or seven of our initiative. So we have the pleasure today to welcome Michele Campisi to talk about his work on measurement of the work statistics of open quantum system using a quantum computer. This is part of the QEI seminar series. So as a small reminder, the Quantum Energy Initiative creates a community that cares for the resource cost of quantum technologies. And Michele is one of us today. And I will leave the floor to him right now. And thank you so much for coming.
Thank you for inviting me. And yeah, I'm happy to have this opportunity here to share with the QEI community, to share with all of you this recent work, which has just been accepted in quantum science and technology. And we are very happy with this work. We are very proud of it. So I hope you will like it too. Uh, So what I'm going to show you is a work on the measurement of work statistics of an open quantum system using a quantum computer. So this is a joint work with Lindsay Bassman-Ofteli, who is a Marie Curie fellow working with me at Institute for Nanoscience in Pisa. She's working on a project called QC for QT, meaning quantum computers for quantum thermodynamics. And in fact, with this talk, I mean, the present research, the research that I'm going to talk to you about today is in fact an example where quantum computers can help advance in quantum thermodynamics. So let me see if I can move on here. Okay. Yes, this slide here is the philosophy of Lindsay's project. We believe that there can be a mutual circle of mutual benefit between quantum thermodynamics and quantum computing. So the two fields can and in fact actually do help each other advance. Just to give you an example uh, of how quantum thermodynamics can help advance in quantum computing, you all know that one basic building block that is necessary for quantum computing is to have uh, um, uh, very well prepared qubit state with very high fidelity. So you want to be able to prepare pure states for quantum computing. You have to have very well prepared initial states. And in fact, in these two papers that you see in the slide, we have studied, we have used thermodynamics concepts and tools, and specifically quantum thermodynamics concepts and tools to come up with methods to uh, create, prepare very highly pure qubits. In one case, we did that using collective cooperative quantum phenomena, and in this other paper here in the bottom, you see my cursor, right?
Yes, no
Moving.
problem.
Yes, this one in the bottom instead is a paper where we used basically dynamic cooling, which is nothing but quantum thermal machinery to cool down qubits and so to prepare them in very as pure as possible. So these are two examples of this arrow here of how quantum thermodynamics can help advance in quantum computing, but also the other way around is possible. So quantum computing can help quantum thermodynamics. And specifically, for example, in this paper here, we have used a quantum computer to verify experimentally some fluctuation relations that were not um, mm, verified experimentally before. So you know that there is a bunch of fluctuation relations around, quantum fluctuation relations. Some of them, they had been addressed by experimental groups. They devised experiments to verify them, but some of them were still missing. And so in this paper, we did what we claim to be an experimental verification of such of some of those fluctuation relations that were not verified at that time. And today's talk is along the same line as in this slide. So we are using now a quantum computer to again achieve something that experimentalists didn't bother to achieve so far, because it's a tough problem, basically, and that's the measurement of of the work statistics of an open quantum system, which yes, it is not been achieved. So we use a quantum computer to achieve that, and of course that in turn can be used to verify the Jarzynski identity and Crookes fluctuation theorem for open quantum systems, which is still missing in the, so to speak, if we have a look at what experiments have been done in this fluctuation theorem business. So let's get to the, maybe I can move, sorry. I just need to make space on my screen. Okay, here I am. So let's move to what is a work statistics for a closed quantum system, and then we will move on to the open quantum system, which is what we are interested in. So in this talk, when I talk about work and work measurement and work statistics, I refer to the two-point measurement, so-called two-point measurement scheme, which is depicted here in this scheme. So imagine you have quantum state that is initially prepared in quantum system that is initially prepared in some state raw, and raw evolves in time according to some Hamiltonian evolution, which is generally here I write as some unperturbed term plus some perturbation v of t that acts over some period of time from 0 to big T. So let's imagine this is a cyclical driving. At big T, you are back to the initial Hamiltonian, and meanwhile, this time-dependent Hamiltonian has generated some unitary U. So the two-point measurement scheme is the following. At time 0, when you start this driving, you make a measurement of the energy. Then your state collapses onto one eigenstate, and you read one eigenvalue of energy, of H0, basically. That's what we are measuring. Then this evolves, and at final time, you make another measurement of H0, you get another eigenvalue, and now you collect, you take the difference between the final and the initial eigenvalue, and you call that work. And if you repeat this preparation, measurement, evolution, measurement procedure many times, each time, possibly you get distinct values of work, each with its own probability, which is written here. I'm sure most of you are very familiar with this expression. So the work probability is a sum of delta peaks centered at the various transitions that are present in the spectrum of your Hamiltonian H0, each delta weighted with the joint probability to observe n at time 0 and m at time final time big T. So as you probably, most of you already know, this joint probability, I'm here now in the bottom of the slide, is a product of the probability to find the eigenvalue En in the first measurement times the probability to jump from n to m due to the evolution u. So basically this Pn is the population of the state n in the initial preparation raw, and this transition probability is nothing but the square of this transition amplitude n then you evolve it, and then you project onto M and take the square. Okay, so this scheme here for closed systems has been actually has been used, and it has been verified experimentally, right? The first experiment that performed such TPM work measurement was used to test the quantum Jarzynski equality for closed quantum system, which in that case was a trapped ion. This paper here dates back to 2015, so 10 years ago. This was the first experimental paper reporting, the measurement of a work probability distribution for a closed system. And a couple years later, there was another experiment, very nice, using like a cloud. This was a sort of Stern-Gerlach experiment. Similarly, in this experiment, they measured the work probability for a closed system. And nowadays, you can do such measurement very easily by yourself, because we have these quantum computers available on the cloud, and you can see quantum computers simply as a quantum system, which I mean, you can see it because it actually is like a programmable quantum system. So you can program it to run basically circuit, and you can, so in that case, in this way, easily measure work statistics for closed quantum systems. Of course, quantum computers are not perfect, so you're gonna measure such work statistics approximately. Okay, so what I'm going to show you is that in fact you can use the same machinery, the quantum computer, also to measure work probabilities for open quantum systems. So let's see, before going into the technicalities, let's have a look at the physics of what's going on when you have an open driven quantum system. So let's look at this sketch. Basically, you have your system here, this pink square. You drive it, so you apply some time-dependent forcing on it, which is here this light blue driving thing. But at the same time, your system is in contact with the big bath, so it may exchange energy with the big bath. So whatever energy you inject in with your drive, so whatever work you perform on your system, it doesn't all go into S. Actually, it goes in the compound system SB. So if you want to measure the work distribution using the two-point measurement scheme, what you have to do is to make a projective measurement of system plus bath at time 0 and get out some eigenvalue here, which here I call E n nu SB. I have two indices, one for S, which is for the system, which is n, and one index for bath, which is nu. And then at time tau, when the process ends, measure again, and you get another eigenvalue, and then you repeat this, and you get the statistics. Beautiful, right? In theory, because in practice, it's basically impossible to do such projective measurement of a system plus, an infinitely large thermal bath. Okay, so this is a reason why two-point measurement is really prohibitive for the open quantum system, despite the theory works perfectly. And one can prove, for example, that the Jarzynski equality, the Crookes fluctuation relation, they all continue to hold true. But as of now, we don't really have a way to measure this global work, apart from very specific cases. So with this research, we tried to get around this problem of the two-point measurement for the open system case. Before I proceed, I just want to mention that in classical physics, you don't have this problem because just like in the quantum case, the work is the energy change of system plus path. But typically, in classical case, you can monitor the system degree of freedom. You can monitor, let's say, this Q here. Let's look at this Q as some degree of freedom in your system, and lambda is the driving, that is the forcing that is uh, uh, um, um, coupled to it. Typically, you can monitor the two of them, and then you can do the integral force, this lambda times Q, which is a displacement. And by looking at trajectories of force times displacement, you take the area below that, and you can get the work done in the open the open system, S plus B, just by looking at S. Okay, this thing is not possible to mechanics because you cannot just continuously monitor the system without really perturbing it. And yeah, you have to do this TPM scheme. But you cannot do it. So let's see how we got around this. So we decided, well, we noticed that in fact the interferometric method, which was put forward in the context of closed quantum systems, driven quantum systems, this interferometric method, in fact, can be used to get around this problem. So the method was first put forward in 2013 in these two papers here that you see in the bottom of the slide. It's two PRL back to back, basically reporting the same method. So I'm gonna briefly, for those of you who are not familiar with it, I'm gonna sketch it very quickly. So closed system, driven Hamiltonian, so H0 plus some perturbation and some evolution U. This is what we want, the probability of work, this object here, which I've described it earlier. So the method actually gets this object here, the work probability distribution, indirectly, meaning that what you really measure with this method is its Fourier transform, this chi of u, which is the characteristic function associated to the work probability distribution. You see it here, that's the Fourier transform of it. And this Fourier transform, in fact, can be written as this double sum, where here those joint probabilities PMN appear. These PMN are these transition probabilities that I introduced earlier. No, sorry. Those PMN are this object here, the joint probability, so product of the transition times the initial populations. Okay, that's what that's what the interferometric method allows you to measure. So it allows you to get this, and once you have this, you do the anti-Fourier transform and reconstruct the work probability distribution. Okay, just very briefly, I want to sketch how this thing works. So you have to couple your system to an ancilla, which is a qubit. And then you have to run this circuit, which is depicted here in the top of the slide. So you prepare your system in the state raw, which is the initial state of your preparation. The preparation, let me go back here. The preparation here that gives you your PN there, that preparation, you prepare it in that state. And you prepare the ancilla in the ground state. You perform another MARD on the ancilla so that you get, coherent superposition of ground and excited state. Now you run these two conditional gates, which I'm going to describe in a second. You do a second Hadamard. And finally, you measure sigma z and sigma y of your ancilla. Okay, so you repeat this many times in order to measure the expectation value of sigma z and sigma y. and now you collect them. You do the sigma z average plus I times the sigma y average. And that basically is the function, is a function g of u, which is basically, and I'm going to show you, and I'm going to show that in a second, this g of u is basically the characteristic function of work that you are after. Okay, so I have still to tell you what are g1 and g0. So g1 is an evolution where a conditional on the state of the ancilla being 1. So if the ancilla is in 0 state, basically it acts as a identity. If the ancilla is in the 1 state, then your system evolves. Your system here, the green thing here, evolves with u, and then evolves with h0, your unperturbed Hamiltonian, for some time u. Okay, the other conditional gate is the other way around. So when the ancilla is up, it acts as the identity, and when the ancilla is in state 1, it acts as the identity, and when the ancilla is the state 0, it acts by first letting evolve your system for a time u with fixed h0, so no perturbation in the Hamiltonian, and then you apply u. Okay, so you see basically you fix this delay time little u here. Okay, you repeat this circuit big number of times. You collect the statistics, and you collect basically the sigma z and sigma y polarization, average value of sigma z and sigma y, and you construct this function g of u. Okay, now you repeat this with many different values of u, and you have the whole function g of u, and this g of u is a closely related, not quite exactly, but closely related to the characteristic function chi of u. So let me show you what is this g of u. So it's written here. It's not difficult to show that g of u can be written in, as the trace of this operator there. It's just a matter of doing the math. And in fact, it can be easily written in this way, which looks very much like the characteristic function, only instead of having here PMN, you have QMN, and the QMN are here. So you see, it's not quite exactly the PMN that I've shown you earlier. Only in the case when rho commutes with the Hamiltonian, so that this n here is an eigenstate of rho, then you get out the population of that state, and what remains there would be the transition amplitude. So it's written here on the right. When rho and h0 commute, basically this QMN coincides with PMN, which means this g of u coincides with the characteristic function of the work characteristic function. And if you do the anti-Fourier transform, then you get the two-point probability, two-point measurement work probability distribution, P of W, which is what you are after. Okay. Okay. So basically, once you have this G of U, you do the anti-Fourier transform, you get this Q of W, which is a quasi probability density. It's not really a probability density because this Q n can be complex. They are not really probabilities. But when rho commutes with h0, those boil down to the joint probabilities of the TPM scheme. And then the function Q of W is the work PDF P of W, which you are after. Sorry that I make this story a little complicated, but this is also something that it was not really discussed in the literature so far. So I wanted to spend a few words on it. This is a issue that that is already there at the level of closed systems. So I wanted to first clarify this point because of course you have the same issue that if rho if the preparation does not commute with the unperturbed Hamiltonian, the method actually doesn't work. And that is true both for the closed and the open case. Okay, so in practice, how do you implement these gates G1 and G0? So Adamard here is not a problem, but how do you implement these controlled gates? How do you implement the Hamiltonian that generates this circuit, basically? So you have to basically implement the Hamiltonian that is written here, this HSA. So let me summarize. This is the problem that you are facing. Sorry, I want to highlight, but it doesn't work. So this is what you want to, this here on top is the problem that you want to basically address. You have this driven system. You want the TP 2-point measurement work PDF associated to this very process. So what you do is you run this circuit, which means you have to now come up with some time-dependent system ancilla Hamiltonian, which is written here, that results in those two G1 and G0 conditional operations. Okay, so let me show you what this all means. So the HSA is what? Is the unperturbed system Hamiltonian cross product identity ancilla. And times here you have some driving, F1 times Q. Q is the operator in your system to which you are coupling, times projector onto the one state of the ancilla. And here you have another driving cross product projector onto the other state of the ancilla. And these two drivings, F1 and F0, are basically, F1 is you drive your lambda of t until time tau, so that you realize basically the evolution unitary u. This guy here, this guy there, this u here and there. And then you keep the H0 fixed for a time, for a delay time small u, so that you realize this. So first the unitary and then this part with fixed H0. And the other F2 is the other way around. You first stay at H0 fixed, and then you implement lambda of t, which implements the unitary big U. So now that would implement this part here. Okay. I hope it's okay. So if you do, and so if basically you run this, in order to create this circuit, you have to run this Hamiltonian. And then if you read the output of your ancilla, you get the G of U, and that would give you the work PDF of HST, this guy here. If raw commutes with H0, if this raw here, if your preparation commutes with this. Okay. Okay, now this is all well known and done previously. So let's now move to the open quantum system case. So what if you do this procedure, but your system was were open? Okay, so the ancilla were closed, and you enact the very same driving. So you enact this driving here, which I've just described. But imagine that your system is not closed; it's open. And the ancilla, in fact, but the ancilla is not in contact with the bath. So in that case, if you apply this driving, so if you do exactly the same, operations in the lab, okay, the Hamiltonian that would describe the dynamics would now be this guy here on top of the slide. So where instead of having H0, now you have some H0SB, okay? So your system is now in contact with the bath, okay? And when you keep H0 fixed, right? It's like you're not doing anything, so your H0SB remains fixed, you know? And when you apply the driving, basically you're applying this thing here where you have F1Q on the system. You're doing nothing on the bath, and this is what happens conditioned on the ancilla being in state 1. And likewise for this other term. Okay, so I repeat, you are an experimentalist. Think about, forget about being theorist. You're an experimentalist and you implement this driving. Okay, if your system is closed, then this is the Hamiltonian that describes your system. If it is open, then this is the Hamiltonian that describes your system dynamics. But if this is the Hamiltonian that describes, system open system dynamics, then it means that the actual circuit that we are implementing is what is depicted here, where this G1 and G0 now you can see them as acting on on the global system bath compound, and just by inspection of the Hamiltonian, you see that this circuit will be such as to encode the function g of u associated to the time-dependent SB Hamiltonian, which is written here, H0SB plus driving on the system times identity on the bath. Okay, so basically you have, let's now look at the same thing backward. Imagine you have an open quantum system described by this. So you have which is basically, it fits with this picture. You drive your system, okay, you act directly on the system. So this is the Hamiltonian that results, where you have this lambda q acting on the system alone. So now here it's written in a better way. I have some unperturbed system bath. I have the driving on the system, and I'm doing nothing on the bath. So imagine you have this open system Hamiltonian. This circuit is such, which is implemented by this Hamiltonian here on top, is such that it encodes the function g of u of this very Hamiltonian into the state of the ancilla. Okay, this was first noted in this paper here in 2013 and basically remained almost ignored. But actually, this very observation is what allow to get around the problem of the work probability distribution of an open quantum system. Because if now you prepare your system bath compound in a state that has no coherencies relative to this H0SB, and you run this Hamiltonian here on top, which means, if your system is open, that you're basically just running the driving on the system alone, then the ancilla will encode the characteristic function of the SB compound. And by inverse Fourier transform, you get to reconstruct the work probability distribution, the 2-point measurement work probability distribution of an open system. So, in other words, if your system, you apply that driving, if your system is closed, you get the closed system work PDF. If your system is open, basically you get the open system work PDF for free. You don't have to do anything. You don't have to know what is the system bath Hamiltonian. You don't have to know what's the interaction between them. If it is open, the ancilla doesn't know if the system that is probing is open or closed. It will just probe whatever is in here. So from the ancilla perspective, it's just probing some black box. And if the system is open, it will tell you the probability distribution of an open quantum system. In fact, by looking at that work probability distribution in the open case, you can get information about the system bath interaction or the bath spectrum. Okay, I'm gonna show you that in a moment. So let me go forward. Before that, another remark, and this again is irrespective of whether you are treating closed or open system. This is a problem that you have in both cases. And the problem is that, from this uh, from this yes from this scheme that I have illustrated, the quantity small u, which is a delay time, is by definition a positive number, right? Positive real number. But which allows you to construct this g of u. But actually, it doesn't allow you to construct you the full g of u from minus infinity to plus infinity. It only allows you to reconstruct that from 0 to plus infinity. Well, of course, it's not going to be plus infinity because you will have, in practice, you will have some cutoff, and also you cannot sample it on the continuous. But you only have, for sure, you can only have positive u's. But for the anti-Fourier, to do the anti-Fourier transform and get back the work probability distribution, you need all u's in the whole real axis. Okay. So this slide is just to tell you that that's not really a problem. Why? Because imagine you have the function g of u, you have reconstructed it only for positive values. So what you can do is this half anti-Fourier transform, the integral now, you integrate that from 0 to infinity rather than from minus infinity to infinity. Okay, I call it the half anti-Fourier transform. It's written in terms of those QMN, quasi probability that I have mentioned before, and then you have these integrals here from 0 to infinity. And this integral formally, you can basically you can write it's basically, you're doing the Fourier transform of a heaviside theta, heaviside step function, whose anti-Fourier transform is written here. You have a peak, delta peak, and a 1 over x peak. So this big P here stands for the principal value of 1 over x. So basically when you do these integrals there, you get for each couple nm those two peaks, a delta peak and a 1 over x peak. It's written here in the bottom, the anti-Fourier, the half anti-Fourier transform of your g of u. You see, you have these QMN that are in general complex, and furthermore, there is the possibility also to have a imaginary part also for this other term here. There is a real and an imaginary part. So the deltas have a real coefficient here, pi, and the 1 over x peaks have a imaginary unit in front of it. So now, for example, you can take the real part of this Q half of this half anti-Fourier transform. It's written here. Again, it's a double sum of deltas and 1 over x peaks, where the deltas are weighted by the real part of the QMN and the imaginary part. Sorry, and the 1 over x peaks are weighted by the imaginary part of your QMN. Okay, so in particular, when rho commutes with h, so when your initial state commutes with your unperturbed Hamiltonian, these QMN are real, and in fact, they are equal to the joint probabilities of the TPM scheme. And then this real part, two times the real part of this half anti-Fourier transform is in fact the work probability distribution that you are after. Okay. And what is nice about this half anti-Fourier transform is that, You have a G of U. You do this half anti-Fourier transform, and you have two types of peaks showing up: delta peaks here, and then you have these which are symmetric around, their center, and then you have one on top of that. You might have 1 over X type peaks with long tails there and an anti-symmetric shape. Okay, so uh, if, so if, for example, if you do an experiment, you get G of U, from this method, you get a G of U. You do this half anti-Fourier transform, and there are peaks like this. Okay, it means that there were some coherencies in your initial preparation. It means that rho and H0 did not commute. If there are only delta peaks, then it means that there were no coherencies, and what you're measuring is a genuine 2-point measurement scheme work PDF P of W. Okay, so basically what we did is we implemented this scheme on the IBM quantum experience computer. And we took for the system a bad qubit. So we carefully chose the qubit to have a very short decoherence time. In this case, the bad qubit, our system had only 38 microseconds of coherence time. Whereas the good qubit, which we used as the ancilla, had basically 10 times the coherence time. So in first approximation, the ancilla, is a closed system, is not affected by thermal bath, whereas our system S is likely much more affected by thermal bath. So it's a good candidate to play the role of an open system. Okay, whereas the ancilla, this good qubit, is a good candidate to play the role of the ancilla. Okay, so we chose those two qubits in such a way that they were, directly connected one to the other. So we didn't have to do, like swaps to connect them. So physically they are closed, but one is very bad and one is good. This is not so easy to find actually, because of course IBM is, fighting to have all qubits to be good, no? So, but we found an instance of a couple which was bad and good, and so we used that to perform our experiment. So we said, okay, what is the process that we want to probe? Let's say the driving U is some random unitary. We chose square root of sigma x. Okay, and we prepared our qubit in the ground state. Okay, so imagining that there is no, imagining that the qubit. So in the ideal case, in the absence of bath, the work probability distribution has only two peaks. In general, there are, right, for a qubit, because either you stay where you are, or you jump up, or you jump down. Okay, but in this case there are only two peaks because we prepare it in the ground state, so there is no chance for you to jump down, right? You are already in the ground state. So ideally there are only two peaks in this problem, with basically with the same height. The two peaks basically contain both 1/2 and 1/2 of the total probability. This in the ideal case. And the peaks are centered in 0 and h bar omega, where h bar omega is where omega is the resonant frequency of the qubit, which in our case was, 4.85 gigahertz. So h bar omega is around 20 micro electron volts. Okay, so let's get to the results. So let's look first at the gray curve. Okay, what is this? This is basically the simulated work probability distribution with a noiseless simulator. So you see one peak here, basically 1/2, another peak there, basically at 1/2, and some little noise here and there. And the peaks are a little broadened, but this is only because we have a finite sampling rate and we have a finite sampling, a finite interval for the whole sample. And the blue line is the actual output of our quantum circuit. So this is what we measure from the IBM quantum processor. Okay, what we are plotting is 2 times the real part of that half inverse Fourier transform. We are plotting, where is it? We take G from the circuit, we do the half inverse Fourier transform, get the real part, and plot it. Okay, so let's look at this blue plot. You see that there are no 1/x antisymmetric type peaks. Okay, so this tells us already that this is a genuine 2-point measurement scheme work PDF. Okay, here in the inset, just for illustrative purposes, we is the same circuit, but same circuit, same couple of qubits, same processor, but we now prepare the system purposely, on purpose. We prepared it in a superposition of 0 and 1, and now you see very clearly this 1/x type broadenings. You see, okay, this tells us that the initial preparation had coherences, and in fact, we did that on purpose. Okay, so this is just for you to see, an example of how those 1/x types peaks look like. So we don't see them. Okay, this is good. It means at least this is a TPM work PDF. But the question is this truly, a work distribution of an open system? Are we really like capturing transitions that are occurring in the compound system plus bath, or was the system actually not really interacting with the bath, and this is just a standard closed system work PDF. So I want to convince you that this is a genuinely open quantum system, genuine open quantum system work distribution. Why? You see, the suspicious peak is this peak here at, basically it's at minus h bar omega. Okay, so what could be the origin of this peak, which shouldn't be there, right? You see the noiseless the noiseless simulator doesn't have that peak, and in theory also we know that there shouldn't be a peak there. Okay, you can tell me, look, Michele, look, it's because maybe your when you prepared your qubit in the ground state, actually it was not really purely in the ground state. It was in a mixture of ground and excited, and therefore there should be here a third term accounting for the possible transition from the excited state to the ground state, which would give rise to a peak. And my answer would be yes. Yeah, that could be one source. So let's check that. So we check what is in fact we measured what was in fact the actual preparation, and it's written here. In fact, of course, IBM doesn't give you the pure ground state. It gives you actually a mixture, and we measure this mixture to be, with this 0.97 probability of being, a ground, and the rest 0.03 probability to be in the up. So basically now we run the same simulation, noiseless simulation, now taking into account this this extra and yes, if you zoom up, in fact, it results in a little peak, but clearly this peak is not sufficient to justify this big blue peak that we actually observe. So there are some other reason why this peak emerged. So one might wonder, oh yeah, perhaps the ancilla was in the excited state, with some probability. That in fact is not gonna have any impact on that third peak, because if the ancilla is in a mixture rather than in the ground state, then your G of U basically just get an overall damping, 1 minus 2 times the probability of the ancilla being in the excited state, which in our case was 0.98. So that this mixture would actually damp all the three peaks. So actually this is damping that peak rather than pushing it up. So this is not the problem. Of course, there can be other, there can be a plethora of reasons why, there is some deviation from the ideal case. But, the very fact that this peak is exactly at h bar omega tells us that, most likely what's going on here is that there is crosstalk between our qubits and the other qubits that are on the chip that have the same resonant frequencies, omega. Okay, so for us this big peak is because our system, the system that the ancilla is probing, is not just what is it? It's not just this system here, but it's actually a broader system with a broader spectrum where there are excitations, and the ancilla, the interferometric method, picks up exactly those transitions occurring in the larger Hilbert space. And this is very reasonable, is because the peak is exactly at h bar, at minus h bar omega, which is one of the which is the resonant frequencies of all the qubits on the chip. Okay, so I think I'm gonna go to the conclusions. Basically, this, to the best of our knowledge, this is the first ever measurement of a genuinely open quantum system work PDF. And by work PDF, I repeat, I mean the 2-point measurement scheme work PDF. The method is actually useful because it provides you information about the bath and the system-bath interaction. Specifically, in this case, tells us that, look, your qubit is actually interacting with other qubits. There is a major source of noise coming from them rather than, from, I don't know, possibly thermal noise from the substrate on which the qubits are patterned, And in fact, it's known that crosstalk is a major, issue in at least in the IBM quantum computer. The method, in fact, since it allows to measure the work probability distribution, it can allow to verify the Jarzynski identity for open quantum system, which is still, an item in the list that is still missing a check. This has not been checked experimentally yet. And of course, now that we know how to measure the work PDF for the open quantum case, we can use it to do that. And finally, it can be used to define noise modeling and improve simulators. And just to justify this last statement, let me show you this graph here. So here, what we did is in red. So in gray is the noiseless simulator. In red is the state-of-the-art simulator, a noisy simulator. And clearly, it shows a little bump, but it cannot use this big third peak. Okay, so the state-of-the-art noisy simulator was not able to reproduce the data. Okay, so it means that the data actually reveal reveal some details about the system bath interaction and the bath, which in turn one can use to refine the simulators. Okay, with this, I think I can stop and take your questions. Thanks for listening.
Thank you so much, Michele. I'm clapping for everyone while they. So, unfortunately, some people have left already because, time goes on, but we still have a few people around. If anyone has a question, you can either unmute yourself and
Yeah,
talk or raise your hand and
I have some
give.
questions, Raya.
Yes, please.
Hi, Michele. It was a nice talk.
Hi.
Yeah, hi. So I just a few questions to just clarify myself. So you said
Yes.
that you were like modeling this for the IBM quantum computers. So they have a different noise profile compared to let's say some other quantum computers. So how do you account for this different architecture then?
Sorry, can you repeat the question? Just the last.
No, your method is actually relying on this certain qubits on this IBM quantum computers, right?
No, it's not relying on that. I mean, we implemented on that, but the
Yeah,
scheme, of course, is portable. You can implement it on any
yeah, but the
platform.
IBM quantum computer has a specific noise profile. So maybe if you implement it on a different architecture, they might also have a different noise structure. So
Exactly. Yes.
you think
And
that, yeah, please.
sorry. Yeah, yeah, please.
No, do you think that it's like generally valid in all the setups or specifically only to IBM at the moment?
No, no, it can be, the whole the procedure is general. I mean, if you apply, if you implement on a different platform, it
Mhm.
will reveal you information about the noise profile of that platform.
Okay.
So here we get, of course, it doesn't really provide all possible information, but it gives you some information. And in this case, it gave us the information about that there is crosstalk going on.
Mhm.
And maybe in another platform, there are other sources of noise. I don't know if imagine that there is no crosstalk, but there is maybe more thermal noise. In that case, I expect rather than another peak, I expect a broadening of the peaks, for
Okay.
example.
Okay. The peak means the one which you spoke about just few slides ago, right?
Not necessarily. I mean, like this is what we got in the specific processor on which we implemented it. But
Right. Yeah.
maybe in another processor, you don't again
You cannot see that. Yeah.
you don't have that, but maybe you have a broadening of the other two,
I see. Okay.
and that would signal that the noise is like that the noise has a higher frequency,
Mhm.
that there is no just a neat a frequency which you pick up here, but that there is like a more of a continuous spectrum that leads to a broadening of your peaks. So depending on how this probability of work will look like, will tell you information about the noise of the specific machine on which you are implementing the protocol.
I see. Okay. Yeah.
Yeah.
Yeah. My other question is, so you constructed this quasi-probability distribution kind of for the work. So that can probably yield negative or complex values, right?
Say it
But
again.
no, you have a
Yeah.
quasi-probability work distribution. So that
Yeah.
might yield negative or even complex values,
Yes.
right? So, but we
Exactly.
know work is real valued. So like when you do experiments, if some complex values emerge, so how would that be
Yes.
made?
So, okay. I- In other words, I'm rephrasing your question.
Okay.
If you are, let me rephrase your question. You are saying, look, this is the outcome of the protocol. What if there are here those 1/x type
Mhm, mhm.
broadenings?
Exactly.
If there are those, it means that those QMNs, they have some complex value.
Okay.
It means that what I am observing is not a work probability distribution function.
Mhm.
So in that case, I mean, most likely you can withdraw, from that thing information about your open quantum system,
Mhm.
but you cannot claim that would be a work PDF.
I
That would
see.
not be the 2-point measurement work PDF. It
Okay.
would be, it is what it is. But it's nice because if there are such things, it also means that you can say that there are coherences in your preparation. So you see, by looking at these plots, you can infer information about the state of your system, possibly of your system plus bath, besides information about the Hamiltonian. It contains a lot of info if you know how to read it.
And that might also like violate this Jarzynski equality if you have a coherence, right?
Sorry?
If you have coherence, that might probably violate this Jarzynski equality, right?
If you have coherences in the initial state, the
Yeah.
Jarzynski equality is not obeyed in general.
Right. Yeah. Okay.
Because Jarzynski equality holds under the provision that the initial state is a thermal state, so stationary, no coherences.
Yeah. Yeah. Nice. Thank you.
Yeah.
Thanks for the question. I don't know if Ariane or Nicola who raised their hand first, so Ariane, go for it.
Oh, okay, thanks. Yeah, thank you for the very nice talk. So I have a question related to how universal this approach is, let's say. So from what I understand, you did it for qubit, for spin-based computers, right? But do you think the same approach could be used for a photonic computer, where you don't have spins as qubits, but then you where essentially you cannot have access to the measure of specific spin or bit, but instead you have a probabilistic approach? Do you did you think of this, or?
I'm not familiar with those, so I'm afraid if I'm gonna answer, I'm gonna say something silly, so let me not answer. I mean, let's say that, maybe I can say something that can help answer that question, even though I'm not really able to say anything specific. So basically, anytime, I think that anytime you have a platform that allows you to do such a circuit like this one, so couple whatever is your system of interest to a two-level system, and perform these conditional gates. I would say yes, you can implement it also on such platform, but I'm not sure about photonic platforms because I'm not really familiar with those.
But what you're saying, if I understand it, rho does not have to be in a two-level system here, but
no.
It can be something much bigger.
Yes.
Okay.
The theory, this theory part, if you go through it, I mean, nowhere. Of course, in the implementation, our system was a single qubit. Yeah, true.
Okay.
We could have repeated it with maybe 2 qubits. We didn't. But this was already, like time intensive because you have to do for each U a big number of runs and then repeat it for many U's in order to collect. So we didn't do that.
I understand. But let's say that formally, from the point of the theory, rho can be any system.
Yes.
Just coupled to an ancilla. Okay.
Yes.
Very interesting.
Yes.
Okay, and then I have another very short question, just to clarify, because I got a bit confused on your very last slide, where you show the two slides. Because when you say you can infer, you can get better noise models. So so the slide just before.
Yes,
you say
this
you can
one.
get. Yes, because here you have a perfect overlap between the noiseless system, which is the ideal one, and the noisy model. So why? I mean, it seems that everything is working perfectly there. So I don't understand the claim.
Yes, I mean, the two, but the problem is that they don't coincide with what we get from the real device. I mean, we should compare those with this blue one where there is this third peak. So this is actually, this blue peak is actually that data that we fetch, and we were not able to reproduce them with any noisy simulator.
I understand.
Okay, sorry, most likely, I was not clear. So Lindsay is, really master of this noisy simulators. She knows everything about them. But with the state of the art noisy simulator, also those provided by the IBM itself, they do not reproduce this peak.
Yes. So what you're saying is that actually those noisy simulators do the same as a noiseless system.
Yeah.
But in reality, you do not have a noiseless system.
Yes.
Okay, I understand.
Yeah, I mean, they don't do exactly the same as you can see
Yeah.
here. These peaks are a little, the red peaks are a little lower, so there is like a leakage.
Yep.
But this is again, more. It's like those simulators kind of. I think like this is my intuition. They spread the noise all over, and after all, you have just all the peaks to get damped,
Yep.
which
Yeah.
is somehow also explained by this formula. But yes.
Okay.
So this experiment can tell a guy who is writing the simulator, look, actually there is this crosstalk there. You try and put it into the model in order to reproduce it. So that would result in a better simulator.
Okay, I see. Okay, thank you.
Thank you.
So, and now Nicholas.
Hello, thanks a lot for the nice presentation. It's really interesting.
Hello.
Can you please go back to the plot where you can see the gray line? The gray line. Yeah, this one. So
This one.
is so the blue one is the data, right?
Blue one is the data. Gray is noiseless simulator.
So I'm guessing that you're extracting the probability distribution function from the real part of Q, right? So it's 2 times the real part of Q here. This blue line, is it?
The blue line is the two times the real part of Q, the half inverse Fourier transform of G. Yes.
So does this one already takes like negative values here? Because it seems to go below 0 at some points. I'm not sure whether it's because of the plotter.
Yeah. It can it can go below 0, even even in the noiseless simulator. But if it does so because of finite sampling, I mean, if you can sample U from 0 to plus infinity on the continuum, then these peaks will be just delta peaks and there would be no negative parts. But because of finiteness of the sampling, you cannot reproduce the the ideal delta peaks correctly, and you always get some giggles or some wavy data around the delta that can get negative value, but those are not really relevant. I mean, actually, we did a little bit of in practice, after you do this anti-Fourier transform, you have to do a little bit of coarse graining along the w-axis in order to get rid of those oscillations. But those oscillations are really spurious, are not really signaling a lack of reality in the QMN.
And here you're always starting from diagonal initial states, right?
Yeah, in hindsight, you see that there are no antisymmetric like feature in these peaks, right? Because if you do this coarse graining, like I said, the anti-symmetry will remain. So after this coarse graining, the only symmetric peaks appear. That tells us right away that that there are no coherences in the initial state.
Okay, thanks. Can you go back to where you show the circuit that implements the protocol?
For example, here or maybe earlier.
Yes, here it's fine. So from what I understand here, your circuit is not implementing exactly the 2-point measurement scheme because it's not projectively measuring the system directly, but it's weakly measuring the system through the ancilla, right? So
I would phrase it in a different way. I mean, it's projective measurement on the ancilla.
Yeah.
Yes.
Right.
So look at it as some maybe you can rephrase it as a weak measurement on the system. Yeah.
Okay.
Maybe.
So for me, it seems like the probability distribution function that you're accessing through this circuit is it's obviously not the 2-point measurement scheme because you're not projectively measuring the state of the system, but it's like a I've seen that this is called the Kirchhoff-Dirac quasi-probability distribution function, or something of the sort, since it's a quasi-probability distribution function that has complex values. So I was wondering if this is the case for that kind of schemes. If you have initial states that have coherences, it's to be expected to have complex or negative values in the probability distribution function. Is it possible to reconstruct this full
Yes,
quasi-probability distribution
yes,
from this kind
yes.
of scheme?
Yeah, it's here. Look, uh, this one in the inset.
Yeah.
So here we prepared it on purpose in a coherent state, and you see that there are these 1/x type anti-symmetric peaks. Okay, so this tells us that yes, imaginary part of, those peaks are of this form. So this QMN, they have an imaginary part. So what we are observing here is a quasi work probability distribution. This one is a quasi probability work distribution. Yes.
Okay, thanks.
Okay. There is also another experimental paper by the group of Nicole Fabri. She has done similar measurements with the nitrogen vacancy center system. So where they have measured similar quasi work probabilities like this, exactly same structure with this 1/x peaks.
Nice, thanks.
You're welcome.
Thanks, everyone. I think except if someone has a very short question, maybe we should stop now because it's been more than an hour already. Maybe I can try to link a bit your work with like the quantum energy initiatives
Please.
Goal, which is like to care for the resource course of quantum technology. So so I know that we have two ways of looking at things, like the very fundamental way, which is kind of what we're doing here now, which is looking at the fundamental cost of quantum operations, and kind of the more practical way of going to see the actual energy cost in joule or in watt of performing certain operations. So how much do you think this work can help us to actually give us maybe lower bounds to estimate the cost of using certain system compared to other
Yeah.
systems? Can you comment?
I think it can, help incrementally in the sense that with an app, it can help, it can contribute an epsilon to the whole thing, because you see, it gives you a way to access the work spent, by the external source in the open quantum case. So, it gives you a new tool. Of course, this is not going to revolutionize the whole field. It's an epsilon, but I hope that, the sum of very many epsilon will help actually achieve some, sensible advancement. So it's just a little step, but yeah, it can help.
Yeah, nonetheless important. Okay, well, I stop the recording now. Thank you so much, Michele.
Thank you all.